Okay, so welcome everybody to this new module of the Smart Grid course. We're going to talk about the communication part of this lecture. So before this, you learned how you acquire data on smart grids, and now we will focus on how we transmit this data to the control centers, for instance, how we can use internet protocols to do that. And later on, when I'll be done teaching you this beginner part of TCP/IP, you will join Jean-Yves Leboudec's group, and you will see more things about security so that you can securely communicate all this acquired data. So the way we're going to work on this is that first I'm going to introduce the layered model of communication, so actually how things are done over the internet using the protocols, TCP/IP protocols. Then we're going to have a look at how we can use all this in our setting of smart grids. And finally, at the end, we will have a look at the performance aspects of all of this. So first, I put the name of an app, Speak Up app, on the side. If you have it, if you don't have it, you can download it on your phone, Android phone. It's so that you can answer such questions anonymously. If it's a pain for everyone to do that, I'm okay to also do it with a show of hands. What would you prefer? Do you prefer app so you can be anonymous, or do you prefer to just answer by show of hands? Hands? It's more simple. Everyone is not shy. Okay. So let's do that. It's also easier for me. So first, what's your section? Who is number one in computer science or communication systems? No one. Okay. What about electrical engineering? Okay, everyone almost. Management? Okay. And you're something else?
Yeah, it's called energy management.
Aha, okay, it's a combo. So don't worry, this is the beginner part, so we will focus on all the important aspects that you need to have, but this part of the course is made such that it's, what?
So everyone here is for the beginner's part, or anyone is for the advanced part? No? Okay.
Okay, because some of the students from computer science already took the TCP/IP course, so we have an advanced lecture in another room, just to make sure that all of you are supposed to be here. So let's dive in. So as I said earlier, you learned how to acquire data on the grid. And now we are going to see how we can communicate this data. So the communication part typically happens between the PMUs and the PDC. So let's see what is this layered approach. So it's exactly when you write software, you typically use modules. You will have a big program that you want to do things with. But in order to make things more manageable, you will typically break parts of the program into functions that you can work on and then interconnect with each other. So the same way we have a layered architecture in TCP/IP. So typically we have these 5 main layers, but depending on the books you can see different layers. But these are the most mainstream one that you will see most of the time. So at the top layer we have the application layer, which is the focus. Which focus is to do the human and machine interaction. So it's a layer that allows you to interact with your machine in a way that is easy for humans to do that. It goes with the transport layer, which will do some transformation of the information that is human readable to something that machines can understand. Then below this, we have the interconnection layer, which allows to interconnect devices. So when you use your phone and you want to communicate with someone else via WhatsApp, for instance, the packets or the messages need to travel across the world. And so all this is managed by the interconnection layers. And finally, we have the distance layer, which transforms bits of information into physical quantities like electromagnetic waves or whatever type of physical quantity is used. So today we're going to dive not too deep, but a little into each of these layers to get a general overview of everything. So the first layer, as I mentioned, is the application layer, which allows you to understand what you're doing. So typically, for instance, if you're on your computer and you press on a link, a page will show up, and it seems to you like everything is local, or maybe you're just communicating with one entity, and all of the internet is hidden from you. You do something and you see a result. So this application layer uses then the transport layer, who will translate everything that you want to do into something the machine will understand. So it relieves the programmer from doing very repetitive tasks. It uses ready-made functions like send and receive. You don't need to focus too much on how to send, how to receive. It's an abstracted layer. So it will put everything that you want to send into a new format. For instance, if you want to send an email, you will have your message, and the transport layer will focus on transforming this message into something that can be sent easily. So the two main protocols in the transport layer are TCP and UDP. TCP is the transmission control protocol. It's reliable, because if you transmit some data from one place to another, it's possible that parts of this data are lost over the network. And TCP is a protocol that makes sure that everything will be received. It will make up for this lost data. This also has a cost, because it means that you need to add some metadata in the packets. So for instance, what it typically does is that it puts numbers in the packets, and the destination will need to send some kind of acknowledgement that it received some packets. And the source will see with the numbers that are in the acknowledgement what was received and what was lost, and maybe transmit again if he thinks it's required. So this is a nice feature, but it also behaves in a not completely expected way. So we say that it offers a stream service because it transforms really the messages into a stream of bytes. If you send many files, for instance, it will send a whole stream of bytes with many files, and the destination needs to understand which bytes belong to which document, which file. So, so we say that the unit of information is a byte. On the other side, we have a second type of protocol called UDP. So these two protocols are the main ones at the transport layer. And it's important to understand that they are not compatible. So the two endpoints that are communicating with each other need to agree on using either TCP or UDP. And UDP is not reliable. So some messages may be lost, and it will not take care of that. So if an application uses UDP to communicate, it means that it needs to do itself the work of handling the data loss if it is required. And unlike TCP, it offers a datagram service to the application. So it means that it really sends the message that you want to send. It will not transform it. So either the destination receives something, in which case it receives exactly what you sent, a message, and not a stream of bytes, or it does not receive anything because it was lost and does not handle this data loss. So what do you think would be a better way of communicating the PMU streaming information? TCP, UDP, or nothing? So who thinks it should be TCP? Okay, who thinks it should be UDP? Okay, so not a lot of answers, but it turns out that the correct answer is UDP. It's better for real-time streaming because so it does not handle data loss, but at the same time it's faster, and we send very small messages very frequently. So if one of the measurements were lost and we try to send it again using TCP, then it will block the new incoming measurements, and the new incoming measurement will make the old one obsolete anyway. So in this case, we can really just use UDP because it's fast and small. So once we have understood the application and transport layer, these packets go through the interconnection layer to be able to travel from one place of the world to another. So in the world, there are billions or zillions of devices, and it's not really feasible to pull cables between every pair of devices that could want to communicate with each other. So instead of this, we use intermediate systems. So the way internet works is very much like the post office. So when you want to send some data, a message, you will send it to, put it in a mailbox, and the postman will come, he will take this message and bring it to the first post switching center, which is closest to you. Then it will reach the destination where you want to send it to, and it will go from post switching center to post switching center until it reaches the one closest to the destination, and the postman will come and give it to the destination. So it's exactly the same in the internet. And in the old days of the internet, we used this type of protocol, which I just showed you, which uses store and forward. This means that the intermediate systems, in fact, all take the whole of the message, recreates it, stores it completely, and then forwards it. And it was okay in the old times of the internet because there were not so many computers and the messages were quite small, so it was okay to store everything and send. But then as technology evolved, we have more and more things to send, and it gets bigger and bigger, and so we had to use new ideas. So this is why a French scientist invented packet switching in 1973. So the idea of packet switching is that it uses the same type of transmission, so still the post office model of working, but all of the messages are broke into packets, small packets which are themselves independent. So if you want to send, for instance, a huge email, this email will be broken into tiny parts of emails, and each of these packets will be like a new postcard with a source and destination address. They will be sent, and then they will be reformed into the email that you wanted to send only at destination, apart from certain exceptions. So depending on the application you use, the size of these packets can differ, but usually the maximum IP packet size is below 1,500 bytes. So the same idea as before, using packet switching, will look mostly like this. So now Bob still wants to send his message to Alice over email. So he will have his entire message broken into chunks, into different small packets that will be first sent to his email server, for instance. And this email server will recreate it and then read what it has to do with it. And it will break it again and send it to Alice's mail server. So these packets will travel through in some of the intermediate systems that do not touch at all the packet. They simply forward it to a new intermediate system, which is the mail server of Alice, who recreates the original packet. And once Alice is available to read it, because she may not be available to read it all the time, so when she's available, she connects to her email web page, and her server will send it to her using packet switching too. So did you notice anything special about how these packets were sent? No? Yes?
They didn't take the shortest way?
Yes, so it's not that they didn't take the shortest path. You should notice that some of them don't use the same path all the time. So this, we try to make sure it does not happen, but it may happen because each of the packets are independent, and every way can lead to Rome, right? So it's the same thing here, but it may still happen. So why do you think do we use packet switching? Do you think it was originally invented to reduce the buffer required in the routers? So the memory that was required in the routers, in the intermediate systems? Or do you think it's to reduce the bit error rates or to increase the capacity? So who thinks it's answer number one? One person. Who thinks it's answer number two? Two people. Who thinks it's answer number three? Way more people. Turns out the answer is number 1. So it was to reduce the memory size that was needed in the intermediate systems. Because if we use the first original way of communicating over the internet, which was using store and forward, every intermediate system needed to store the entire message. So here we have a space-time diagram where we have time on the vertical axis and space on the horizontal axis. So notice that the messages travel from place to place according to a diagonal line. It's not straight because it takes time to travel from one place to another. And once you are the intermediate system, it has to wait for the entire message to arrive before deciding what to do, to forward it. And it takes quite some time. Whereas with packet switching, you receive a part of it and you can directly send that part to the end point. So in terms of memory, you don't need as much memory space all the time in the intermediate systems. And also it reduces the latency, the delay that it takes to send the overall message. The capacity can in fact be increased because it requires some work to use TCP. Typically, you need a handshake to make sure that the two entities agree on speaking together using the same protocols. And you need to send more metadata to handle the data loss and things like this. So yeah, it was mostly for this buffer size to reduce the buffer size. Here you have a snapshot of the Epfl IP network some time ago. So you see devices, endpoints, and these oval-shaped things are routers. And in between them you have lines which are interconnecting the routers to the devices. And you see that at every line from the routers you will see an address. So we use IP addresses, which allows you to understand geographically where are the devices, where you want to send your information. So it's exactly the same as if I want to send you a postcard, I need to know your postal code and your address. So the same information, but for computer networks, is encoded in the IP addresses. Typically, we write them in decimal format. But in truth, they are handled by the machines as bit strings. So typically an IPv4 address is 32 bits, which are broken into chunks of 8 bits. So 128 is a decimal representation of 8 bits. So these 32 bits addresses were the version, the typical addresses for the version 4 of IP. But we have, so this was the old version. It has quite recently changed to IPv6. And the main reason for this change was the address space. So with 32 bits, you can only encode 2 to the power 32 unique addresses, which seemed like it was really a lot when it was created because there were very few computers in a few universities, and that's it in the world. But nowadays we all have several devices, and we will soon be a lot of people on Earth with a lot of devices. So we don't have enough unique addresses possible for all of these devices. So a new scheme was, a new numbering plan was created, and it's in IPv6. And now the address space is 128 bits. So before we used decimal notation, but now we use hexadecimal notation. And these are typical IPv6 addresses. So the 128 bits are broken into chunks of 4 hexadecimal digits. So this is a typical Epfl public address. So we have to differentiate private from public addresses. So usually we use public addresses to be able to communicate over the internet, over the public space. So with this, people will understand where you are physically in the world. The prefix of this address is 2001 because it was standardized in 2001. 620, 618 corresponds to Epfl. So if you're somewhere in the world and you see 2001, 620, 618, it means that you have the IP address of someone who is at Epfl. 1A6 is a subprefix which shows where in EPFL this computer might be. And then the rest is more stuff. So these IPv6 addresses are quite big. And so we need some ways of compressing them exist. So we have to follow some strict rules. For instance, in every piece, you can remove the leading zeros. So for instance, in this address, you have 0620, so you can remove this 0. You can also remove this one. And here you can remove all of them, all of the leading zeros, and keep only one. And if you have lots of pieces with only zeros consecutively, you can remove all of them and put 2 semicolons instead. So this is this rule. But this can happen only once in the address because you need to be able from the compressed version to have the unique possible complete address, not compressed. So if you use twice the semicolons, for instance, you will not know how many zeros should go first, how many after. So you can use it only once. Here we have some possible IPv6 addresses. So who thinks that the first one is a valid IPv6 address? Okay, who thinks it's not a valid IPv6 address? Okay, why?
There should be a semicolon after 2018 because there are not sufficient zeros otherwise.
So there are not sufficient zeros. The semicolon could be a bit anywhere in there, not necessarily after 2018, but typically here there are some missing pieces and we don't know where. Is the second one a valid address? Come on, I'm sure someone can answer. Yes?
There is 2 times.
Exactly. So we don't know how many zeros should be put where. The third one? Yes, the third one is a valid IPv6 address. Okay, so there are some principles in IP that should be followed. And the first one is that we use structured addresses, as I just showed you. And we know where to send a message when you look at the destination address according to some forwarding tables. So when the message arrives to an intermediate system, it will look at the message, see the destination place, and it will know where to send to depending on a routing table that it will have. And for this, it uses longest prefix match. So here is an example. We have 3 devices communicating through 4 routers, which each have their own forwarding table. And for instance, if Alice wants to send a message to Bart, when the message arrives at router 2 will look at this message and see the destination address, which is b.d.h2. And in the forwarding table, it uses the longest prefix match. So it has b or b.d, and the longest prefix is b.d, so it should send to interface number 2. How do you think would R2 route a packet for Homer? Does someone want to answer that? So now we changed the routing table at R2, so we don't have a B here, we have a star. Star means anything possible. So it would be the default gateway, the default output option. And so in this case, b.c.h2 will not match with b.d, it will not match with A, so it will go to interface 3 to the default gateway. So we can use this type of aggregation in the routing table such that we don't have to have a rule for every possible destination address. So it allows for compressed routing tables. And usually it's good to have a default gateway, because if a router receives a packet which does not match with any of its rules, then it will just drop it and send an error message back to the source, but it will just drop it. So yeah, I answered this question. If there is no rule matches, it drops the packet. So usually it's good to have what we call the default gateway, and we will see this in the lab. Second IP principle is that we should try to communicate with devices that are close to each other without using routers, without using intermediate systems if it's possible, to communicate directly if it's possible, and if not, then we use the internet and we use the routers to interconnect subnetworks. So in this example, we have two LANs. So LANs are local area networks, which are a synonym of subnetworks. One of them is communicating through a Wi-Fi base station, and the second one through an Ethernet concentrator. So if computer B wants to communicate with the phone E, it can do so by going only through the Wi-Fi base station. So it does not need to go through a routing table or anything. It can just directly communicate with each other. Same if W wants to communicate with the printer. But now if W wants to communicate with E, it has to go through the router and to use IP. So if we don't use IP, we can, there is something else that we will talk about later. It can use only the MAC layer, which was below the network layer. And it does not need to use all this IP thinking. So now consider that we, from W to P, we send a message from W to the printer. So in a local area network, we don't have to go through a router to another local area network. What would you think would be the IP destination address that we would see in the packet here at 1, so before the Ethernet concentrator? So who thinks it should be the IP address of the printer? Okay. Who thinks it should be the IP address of the Ethernet concentrator? No one, okay. Who thinks there is no IP address because anyway we don't use IP but just MAC? Okay. So the answer is A. We use the IP address of the printer, and it is true that it would be really tempting to say that we don't need IP because we actually don't use IP. But we still need to put the IP address in there because otherwise you would need to you will need to have two different softwares in your device to handle whether you're communicating to someone close by or someone far away. But for it to be generic, you make sure that you're able to communicate with everyone. And this is why you still need to use IP. So this is also because it was made like this a long time ago, and it has to, and it stayed the same way. In IP packets, we have headers, and in the headers, we have some extra information important. So one of them is what we used to call, what is called now the hop limit, but used to be called the time to live. It's a number that is put in there, and so when a packet is transmitted is forwarded by an intermediate system, it will decrease this time to live. So each time the packet goes through a hop, this number decreases, and if it is at a minimal value, the intermediate system will not be able to transfer this message anymore. So the purpose of this field, for instance, is to make sure that packets that are trapped in loops will not go on forever in the network, but will be just dropped at some point. So the minimal value of the hop limit is 1. If a packet is received with hop limit 1, then the device that receives it is not allowed to transmit it, to transfer it. So it will look at it, and if it is for him, then good, he will analyze it. But if it's not, he will just drop it and send back an error message to the source. And if we do not do anything, the default hop limit value is 64. So this field is used in a command called traceroute, which you will also see in the lab. So this command allows you to see which intermediate systems are used to connect to a particular endpoint. So for instance, if you are here at Epfl and you want to send messages to Google, you can do traceroute Google and see all of the intermediate system along the way. So the way this function works is that it uses the field of the hop limit field. So first it will send the packet to Google with a hop limit of 1. And so it will be received by the first intermediate system, who cannot forward it. He knows he has to forward it because is not corresponding to the destination address. But the hop limit being 1, he cannot forward it, so he will drop it and send an error message back to the source. And now the source knows who was the first intermediate system. Then the source will send the same message again, but this time with a hop limit of 2. So it will go through the first intermediate system to the second one, who this time will also drop it and send back an error message. And it goes on, and at the end, the source knows all of the intermediate systems that were used by your packets to access to the Google servers. The end-to-end principle in IP states that any layer that is above the network should avoid using intermediate systems. So these intermediate systems should only be used by the network layer, by the IP layer. Which means that it should be invisible to you when you're using the application layer. You should have this illusion that you're talking only to the endpoint. If you're over a Skype session, you have the illusion of talking directly to this other person over Skype. And maybe it uses intermediate system, but it should be invisible to these upper layers. However, sometimes in life, IP principles in general should be used only if it helps you. If it does not, then you can think of other ways to work around. So sometimes this end-to-end principle is not always respected. For instance, what do you think the end-to-end principle would be for email? So we have A and B who want to communicate via email. They each have their own email servers. How do you think the end-to-end principle should be applied here? Don't be shy. Okay, be shy. So the idea would be that normally A and B should be directly communicating together without going through intermediate systems. But as we have seen in the previous examples, when we use packet switching, the email servers were gathering all of the packets and reforming the original message before sending it to the endpoint. The idea here is also that B, it could be like a phone, and you're not always here available to read your messages. You want to read them when you're able to do so. So because of availability, you will typically send it to the server, who will store everything for you and send whatever you received when you are available. So in that sense, this would be an application layer intermediate system. So it will close the TCP connection, regroup the message into one single message, and then send it to you at another time. So it means that it will open a new TCP connection from the server to the end device. Yeah. Another type of, yes?
Then, what you said before, almost no service goes by the rule that you just said. It's almost always a server.
A lot of the times, yes, and we will see even more examples where this principle is not applied. But if everything was working well to make the internet, it would use these IP principles, but sometimes you need to change it for security reasons or availability reasons, and we will see more of these reasons. For instance, this is a typical reason. So in IPv4, we saw that there was only 32 bits IP addresses. So it was not a lot not enough to have enough unique IP addresses. So a device was created, which is called a NAT. It's a network address translation box. It sits in front of a LAN, for instance. So if you're at home and you have many devices, you may use private addresses within this subnetwork, but you cannot communicate to the internet with it. So Swisscom would not give you many public IP addresses, but only one, which would be the public IP address of the NAT. And all of the incoming and outgoing messages would have to be translated by this NAT, so the IP address would be transformed. For instance, if A or B wants to communicate to the internet, it will send its packets as if it's normally sending to the internet, but it has to go through the NAT. And the NAT will change the source address of B with his own source address. So it becomes a public address. In that way, we have these two devices that can communicate over the internet with one single public IP address. So this is typically used in large companies that have large intranets. They cannot afford to have public IP addresses for everyone, so they typically use NATs. So the way the NATs can differentiate incoming messages that are targeted to A from incoming messages that are supposed to be given to B is by using port numbers. So port numbers are like interface numbers. If you are using your computer and you're using many applications on your computer, for instance, you have Skype, WhatsApp, Facebook, many different things on your computer, and you receive messages, your computer needs to know to which application to send it to. And for this, it uses these port numbers, which are like interface numbers. So in this example, for instance, we could imagine that A and B are both having a Skype session over the internet. So on their own computer, they are using the same port number, 1029. So it would be very hard for the NAT to differentiate the two incoming messages for the two different destinations because they use the same port number. So the NAT will give them his own public IP address, but he will assign a new port number to each of them. And he needs to make sure that there are no collisions in this choice of port number. And he needs also to make sure that he remembers this choice. So he will store these numbers. And if messages come to his own public address with the port number 3442, he will look up in his table and he sees that it should go to B. And so he will translate these messages. So it means he will really physically change the source or destination IP addresses in the packets. Another type of intermediate systems that go above the network layer are the application layer gateways. So this is really also not respecting the end-to-end IP principle. These are typically called web proxies also, for instance, and they sit in the middle. Usually they will be in front of the intranet. So if someone in a company, for instance, wants to access to YouTube videos, it may be that the company has decided that their workers are not allowed to go to YouTube. So they would install typically a gateway, and all the requests for the public internet would have to go through this gateway. And this gateway will terminate the TCP connection, retrieve all of the messages, understand them fully, and then decide whether they want to accept it, in which case they will forward, open a new TCP connection over the internet, and they will play some kind of man in the middle. Or maybe they will not accept it, and then they will just terminate the TCP connection. So can you mention any good reasons for wanting such an application layer gateway?
Avoiding malwares.
Huh?
Avoiding malwares.
Yeah, for instance, it could be one reason. So it's a security reason. Any other reasons? So there are several of them. There is mobility and availability that we mentioned earlier for the email example. Security and access control, typically for companies or avoiding malwares. For interworking also between IPv4 and IPv6 because they are incompatible. So if two endpoints want to communicate, but one is only able to communicate in IPv4 and one only in IPv6, typically it will need an application layer intermediate system to do the link between them. And it can also be used for performance aspects because typically this gateway in the middle can cache information. So if a lot of people in the company always ask for the same thing, the gateway may cache this information and send it again from a closer point without requesting it over the internet. An example of things that use application layer gateways or firewalls exactly for security reasons. The simple firewall is the only one device firewall, so they are easy and simple to monitor, but they are also a single point of failure. And when there is a lot of traffic going from the intranet to the internet, it may also be a traffic bottleneck. So usually for bigger companies, we have more advanced schemes like this one, where we have routers before and after the application layer gateways, and these routers will filter the communication. It will allow some of the messages to be transferred, or will drop some that by default should not go through, for instance. So this was about application layer gateways. We saw that to send messages, we need to know the IP address of the destination address. But most of the times, you don't know by heart the IP address of Facebook, for instance. So you don't type like the numbers of Facebook, but you just use the names. So we have this other naming scheme, which makes it easier on humans. It uses human-readable names. And typically, one name may have several IP addresses, and some IP addresses may not even have a name. The last two letters are usually a country code, like CH, but I think you know that, or .com, for instance, 3 letters, or for more historical reasons, because before it was used only for commerce. We're going to start again. So welcome back. As I mentioned earlier, so we use IP addresses to send messages from one place to another, but to make things easier for the human, we also use names. And the names and the IP addresses are linked to each other, and in order to know which IP address corresponds to a certain name, we use DNS servers, domain name servers. So typically, if you're on your computer and you click on a link on the name of a certain web server, you click on it and your web client wants to access to the web server, but first he needs to know which is the IP address of the web server. So for this, he will first, when you click it, he will first ask the DNS server who is, for instance here, ssc.epfl.ch. And the name server will answer with the IP address of corresponding to what Alice was looking for. And then the web client on your computer is able to communicate to the web server that he wanted to communicate to. And the latter can answer back with the web page that you were requesting. So all this happens very fast, but this is the behind the scenes of your everyday computer usage. So below the network layer, we have another layer which allows for interconnection that I mentioned a bit earlier, which is the MAC layer. MAC stands for Medium Access Control, and it allows devices which are close to each other to communicate directly with each other without going through routers. So for instance, in the first example that I showed you before, we had 2 LANs which correspond to sub-networks, so local area networks. And one of them was communicating through a Wi-Fi base station and the other through an Ethernet concentrator. So the way it communicates is that it uses MAC addresses. So MAC addresses are hardware addresses. They are unique and unique to the computer, so it will not change like the IP address that changes if you travel somewhere in the world. It's very unique. So it's exactly like for me, when I was born, my parents gave me a name, Marguerite, and this will never change unless I have really issues with it, but it will not change. And but I was born in Singapore, I lived in France, now I live in Lausanne, so my postal code has changed, my postal address has changed. And this is exactly the same with the IP address and the MAC address. And if someone knows my name, for instance, you can know my name and you want to tell me something, we are close enough to each other that you might just say my name and maybe shout the information. I know that it's my name, so I will listen to you and I will process the information that you're sending to me. But the others who knows that this name is not their own name, they will probably just like put it aside. So it's exactly the same way that it works in using MAC between devices. So typically, you will use the address to just shout, so it will broadcast the information to everyone, and only the person with the right MAC destination address will keep the information and process it. So this is the simple way. Maybe the messages will be encrypted if you think about secure communication, but this is how it works. So if you're at home and you have several devices that work with the same Wi-Fi station, in principle, when you try to access the internet through this, the request will be sent to everyone in the LAN, and only the gateway will process the information and send it along. But your brother's computer might be able to see what you're requesting to the internet, for instance. So the way, this is exactly what I explained. So you send it to everyone, and no one keeps the information unless their MAC address corresponds to the destination MAC address of the received messages. So you notice that in both of these LANs, the router belongs to both of them, because routers are here to interconnect the LANs, and they can have several interfaces. So on one interface, this router can belong to this LAN, and on the other, it can belong to the other LAN. So that's how we can use them to interconnect the local area networks. So in order to communicate with other devices on the same LAN, the devices need to know which other devices are on the same subnetwork as them. They need to understand if they have to go through a router or not. And so typically the computers or devices that are in the same subnetwork will have the same network mask. So the network mask is the prefix of the IP address. So for instance, in this part of the network, we can notice that the whole the first three groups of digits are the same. So they correspond to the MAC address, no, not the MAC address, this network mask of this local area network. This is, of course, for the IP address, because the MAC address is the hardware address. So the beginning of their IP address must be the same, and we know your device will know how many first bits to look at to know whether the other device is in his LAN or not. So for instance, at Epfl, the first bits that correspond to the network mask are the first 21 bits. But it's not always the same, because for instance, at ETH, I think it's 26 first bits. So in order to know who is in the LAN and to find out the MAC addresses of the other devices surrounding you, we use what is called the address resolution protocol. So ARP request and ARP replies. So one host will send an IP packet to the other hosts, and only the one corresponding to the person whom you want to communicate will answer if it has the valid IP address that you're looking for. And when he will answer, he will also have his own MAC address in the message as source address of the message. And therefore, you will now know the address, MAC address of the people surrounding you. Did you understand that? It's called the neighbor solicitation protocol. And then below this interconnection layers, you have the physical layer, which simply transforms bits and bytes into waves, electromagnetic waves. And so there are some people that focus on this type of research. This is not really us. But what is important to us about these signals is how many information can they carry in how much time. and usually how much error or noise there can be in these signals. So this is the only important part for us in the physical layer, we would say. So this is all I wanted to say about all of the different layers. But now let's try to have a look at what happens when we put everything together in one simple example. So in this example, we will have the web server, so the computer in blue at the top, from one LAN, who will communicate with Elaine, so the phone, which is in another LAN, by going through a router. And we will look at these messages layer by layer to see what happens. So we are first at the web server's application, who decides to send some message to Elaine's application. So first thing is that the application will say to its transport layer, I want to send this data block with this S2 interface. And the transport layer says OK, and he hides the fact to the application layer. He hides the fact that this data block will in fact be broken into other chunks, smaller chunks of data using packet switching. So this big data block is here separated into 5 smaller blocks. And so the transport layer gives this to the network layer to say, OK, now I want to send these small blocks to this person. Please do the job. And the network layer will say, OK, what do the DNS request, everything, to find out the IP address of the person. And he will know the IP address of Elaine, so the green address, and put it in the IP header to these packets. So now we have these little postcards with the parts of the data and the destination IP address. The MAC layer will want to transmit it, but he is not close enough to Elaine's device. So he will know he has to first send it to the router, and the router will later transmit this information. So before going to Elaine, he has to use the MAC layer to communicate with the router. And the MAC layer will add them as in a header the MAC address of the router. And then the physical layer physically sends this information into, by transforming it into electromagnetic waves, for instance, and it will be received by the router. The router sees that the MAC destination address is its own, so he will keep this message and really proceed further to analyze what he has to do. And it will remove this header, this MAC header, and see the IP header. And then he will notice that the destination IP address is not his own, because his network IP address is a gray thing, but in the IP header it's green, so it's not his own. So he knows he has to forward it in Elaine's direction. So he will use his routing table, and he will look at what is the next person that needs to receive this in order to send it to Elaine. And in fact, in this example, it's directly Elaine. So he will send back these packets to the MAC layer, who will change the MAC header into Elaine's MAC address, and the physical layer will do the rest. And Elaine, when she receives these packets, her MAC layer will see that it's her own MAC address. So she receives the packet, she removes the MAC header. She sees it's her own IP address, so she keeps it. She does not add a new MAC layer address and send it along. She keeps it. She removes this IP header. And the transport layer receives these chunks of data that needs to be aggregated back together into the original format. And if it's what was requested by the application, for instance, WhatsApp, it will issue a read to the application of Elaine, and Elaine will see in a human-readable format the data block that was sent by the web server. So this is the general overview of everything we've seen this morning. In terms of terminology, I kept saying packet, message, data block, and it's a bit complicated to remember everything, but usually when we talk about these chunks of data at the transport layer, we talk about TCP segments. Below at the network layer, when we add the IP header, we talk about IP packets. And with the MAC header on top of it, we talk about MAC frames. So typically people, like devices at different layers. So a layer will offer a service to the above layer. And entities that are on the same layer, they communicate with each other using a protocol, so very well-defined rules. For instance, at the transport layer, it's TCP. At the network layer, it's IP. They use well-defined rules. So let's have a look at the onion view of all of this. So we saw the general thing that is transmitted is a MAC frame. And in the MAC frame, we have the MAC header with many information, including the destination and source MAC address, and a MAC payload. And this MAC payload is the IP packet, which also has a header with the address, all the metadata important, and an IP payload, which corresponds to the TCP segment, which has the header and a TCP payload. So in the headers, we have lots of different things, usually the destination and source addresses, and for instance, the hop limit and other type of information that might be important. For instance, in the TCP header, it will say, in the transport header, it will say whether we use TCP or UDP or things like this. And the TCP payload will be just the bytes of information that you're trying to transmit. So this is a pretty display of such headers altogether. So of course, when you send the information, it's just bits and bytes of information. It's not as beautiful as this. But in the lab, we will use some software that allows you to intercept packets and see what's inside. And typically, it displays nicely what is transmitted. So for instance, here the source address is an IP address, but there is a name. When you transmit it, there's not the name. It's just that before printing, we did the DNS request. So let's say now that we observe a packet from the web server to LN, so it has to go through the router, and that we intercept a packet at 1 here, so before the router. What do you think is true? So is the destination MAC address the MAC address of the router? Who thinks it's yes? Come on, don't be shy. 1, 2, 3, 4, 5. Good, that's correct. Who thinks that the destination IP address is the IP address of the router? No one. Okay, that's also correct. It's not the case. So only if the first answer was correct. So now we will look into, through an example, simple type of exercise, how all this is used in our setting of smart grids for PMU to PDC communication. So in our setting, we have a smart grid, and we have some kind of a grid parallel to the smart grid, where the PMUs are interconnected via switches or routers to the PDC, for instance. So switches are intermediate systems that will not, that are quite invisible. Yes?
What is a PDC?
It will be the control center. So typically, you will take some measurements. The PMUs will take some synchrophasor measurements, and then they will send it to the PDC, who will take make some decisions of what to do next. So it's at the PDC, for instance, that you will understand the state of the system, and then takes some decision of attribution of energy. So typically, what we're interested in is how do we send the information from PMU A, for instance, in this example, to the PDC. So let's say that originally, at time t, we see a packet at switch 1. It's the very first packet. Nothing else was transmitted here before that. So what do you think will be the type of this packet? Who thinks it should be a DNS packet? Okay. Who thinks it should be a HTTP packet? Okay. Who thinks it should be an ARP? Okay. And who thinks it's none of this? Okay, so I think there were more answers for the ARP request, which is correct, because before sending the message from the PMU to the PDC, you need to find out who is around you, the MAC addresses, so that you can actually do something and communicate with someone. And some people answered DNS. So with DNS, you will ask for the IP address of the PDC, which is required, of course. But to be able to talk to the DNS server, you first need to find out the MAC address of the router. So this is why we start with ARP. Now, let's say that this packet, Okay, so now we sent the ARP request. We received the ARP answer, so we know the MAC addresses of the people in the local area network. And PMUA sends another message. So what do you think will be the field in the application layer header of this packet if it is intercepted at switch 1? Do you think it's HTTP, TCP, or DNS? Okay, let's start. HTTP. No one, okay. TCP. DNS. Okay. Or none of them? No. So the answer is DNS. So it's exactly as I mentioned earlier. After the ARP request, we ask the DNS server a new request, which is what is the IP address of PDC. So what do you think is the transport header of P0, of this message? So now we saw that at the application layer, it's DNS, because we want to communicate with the DNS server. But for this, the transport protocol use the protocol. And what do you think it is? Is it TCP or UDP? Who thinks it's TCP? Okay, who thinks it's UDP? Correct. It's UDP simply because it's a small message. We're not sending huge bytes of a file. We're just asking a small request, which is what is this IP address? And it will send a small message back, just an IP address. So we don't need a whole reliability scheme for this. And what would be the source IP address and destination IP address at this packet? So we are at switch 1 before the router, okay, and we are sending from PMUA to the DNS server. What would be the source and destination IP address? So do you think it is the source of PMUA and the destination of the DNS server? Yes, yes. Okay. Who thinks it's the source, the PMUA IP address as source address, but the routers at this interface IP address for the destination? No one. And who thinks it's the source PMUA IP address and for destination the PDC IP address? Okay, so remember that here we are not talking yet with the PDC, because at this point we are just requesting the PDC's IP address. So answer 3 cannot be possible because PMUA does not even know the IP address of the PDC. This message is just between the PMUA and the DNS. So the first answer is correct because you're sending to the DNS server your request. Now what about the MAC address? So who thinks the source MAC address should be PMUA's MAC address and the destination should be the switch? Okay. Who thinks that the source is PMUA but the destination is the router? Okay, one answer. And who thinks that the source should be the switch and the endpoint should be the router? No one. And what about PMUA for the source MAC address of PMUA and destination MAC address of the DNS? Okay. So in this example, the correct answer is PMUA and router and the router's MAC addresses because so we are sending an IP packet from one LAN to another. So as we saw earlier, the IP addresses have to travel through LANs. So the source IP address was PMUA and the destination the DNS. But for this, it has to go through the router, which will interconnect the LANs. So the MAC address, which is only at the MAC level, will be the one of the first intermediate system it will go to. So in that sense, it would be tempting to say the switch, but the switch is just a repeater that does not alter anything. The router, on the other hand, will receive the packet and then send it to a new LAN. So in this example, the source MAC address is the MAC address of PMU-A, and the destination MAC address is the MAC address of the router. Is it clear for you, this difference between switch and router? Yes? Okay. Not so much? Yes?
So a switch just connects the elements inside of the same LAN, and it doesn't happen to have its own MAC address. It just repeats.
It just repeats. Yes, it's just like a loud amplifier, you know. It receives things and retransmits without touching them at all. Whereas the router will change something. It's an intermediate system that will forward things to a new place. It will itself decide where to transmit to. The switch does not look at the addresses or the destination, it just says things. The router will look at his routing table and decide to send that it receives from here, but to send on this interface. It will do something. And so in that sense, it also needs to change his MAC address because it was just a destination intermediate system.
Can the switch be seen as the Ethernet concentrator?
Yes. It's the same for a Wi-Fi base station or for the Ethernet concentrator. Yes. Okay. So now let's say that the DNS server replies with the answer. So now PMU-A knows the MAC address of everyone in the LAN, and he knows the PDC's IP address. So the next packet is really about sending the synchrophaser data from PMU-A to the PDC. And now we are at router 1, and we intercept this message containing the measurement. So what do you think would be the application layer header? Who thinks it's HTTP? Okay. Who thinks it's TCP? Okay, so TCP, it cannot be the case because right now I'm talking about the application layer. And TCP is about the transport layer. So TCP could be maybe the case in the TCP header, but not application layer. Who thinks it's DNS? So it cannot be the case because we already did that. We already have the information. Who thinks it's this weird number and letter? Yes. So in fact, it's this weird thing, but you cannot have guessed. It's just the name of the standard for PMU to PDC communication. So now that we are looking, now we look a bit below, we look at the transport header. Okay? So who thinks that the transport header is TCP? Okay, who thinks it's UDP? Okay, so it is UDP. Can someone explain why it's UDP and not TCP? Exactly. TCP will need to handle the lost data and resubmit. And before resubmitting, it will stop receiving everything. So it will just have a huge latency and everything will be outdated compared to the live evolving state of the electrical grid. So typically, I think if I remember right, you would take measurements every like 20 milliseconds in the smart grid. So it's very fast. And it's a tiny measurement, a complex value. And so you will just send this, and they will make the previous measurements obsolete. So you don't need to focus on retransmitting anything. That's why we use UDP, which is typical for live streaming. What would be the source and destination IP address? Who thinks it's answer 1? Who thinks it's answer 2? And answer 3? Aha, unanimous. This is correct. So now we are still at router 1, intercepting the same message. What is the source and destination MAC address? So who thinks it's answer 1? No one? Who thinks it's answer 2? Answer 3? Answer 4? Answer 5? Okay, everyone is quite shy about this question. Is there something you did not understand about the MAC addresses? So remember, the IP address goes far away. It follows the end-to-end principle of IP in general. So it will be from one endpoint to the last endpoint. So PMUA to PDC. But the MAC address is a bit lower, and it handles things that are close by to go from one place to another. So now it means it's the router 1 is the first intermediate system. So you need to put the MAC address of this intermediate system. You see? So this is why the third answer is the correct answer, because the source of the message incoming is PMUA. PMUA had this measurement and is trying to send, and it will have to go through the router. And so the destination MAC address is that of the router. Okay? Now, the routing rule matched at R1. So how does the router know that the message coming from PMUA has to go on this interface and not this one, for instance? Who thinks it's number 1?
What is the /16?
Okay, the /16 is the network mask. So it means that everything, it's not, it's like, but if you check the first 16 bits of 10.1, because 10 and 1, this is in decimal format, but you need to translate this into bits. And if you have /16, it means if everything, if the 16 first bits correspond to this, then send to that interface. So with these numbers, I'm asking which rule would be followed, keeping in mind that we use the longest prefix match. So will it be 10.1 or 10.2 or 10? In fact, this quite depends on the routing table, which is not displayed here, so I think it must be quite hard to answer like this. So let's have a look at a possible solution for that. So let's say that the routing rules at R1 are these, here. So 10.10 followed by whatever comes next will have to go to the north interface, so this interface. 10.1 will have to go to the west interface, and then 10.5 or 10.2 will both go to the eastern interface. So, as I said earlier, the IPv4 addresses are in decimal format, but to answer this question, we need to switch to strings of bits. So if we translate 10.10 in bits, it looks like that. So we have the first 8 bits corresponding to 10, and the second 8 bits also corresponding to 10. 10.1 will be translated as such, and 10.5 and 10.2 are these. And these can be aggregated further. So from 10.10, in fact, if you notice here, there is no other possibility where there is already a 1 here. So it seems that whatever we look at, if we stop here and it works until here, if it matches until here, then it should go to interface N, the north interface, because there is no collision, no ambiguity with the others if we stop there. So this can be reduced to this address where we checked only the 13 first bits if we stop at the first one, and then we don't care about the rest, so it can be zeros or whatever. This one, well, the 1 is at the end, so we cannot do much about it. We keep it this way with /16. This one is the same as for here. If we stop at this one, we don't have any more ambiguity with the rest, so we could stop searching at this point, which correspond to just 1, 1 and /14, just checking the first 14 bits. And for the last one, we have the same reasoning. We just have to stop at the bit number 15. So this is a bit more simple way of looking at these addresses, but we can do a bit more. So this one we cannot change it really. This one also we cannot. But we see that there are two addresses that go to the Eastern interface. So maybe we can look at a way to aggregate them together into one single rule. So in this case, we could say that whatever starts by 10, if we checked only the first A bit, should go to the Eastern interface, because then it would mean every address that starts by 10 which does not follow these two rules. So since we use longest prefix match, if something matches this or this, it will not match this, because this will come later as it is a shorter prefix. Okay? And then this, we would rewrite it in decimal. As I was saying, now we have routing table rules that are still written in bit strings, but now we can rewrite this in decimal format, which will look like this: 10.8/13, 10.1/16, and 10/8, which will go to the Eastern interface. So now in our example, if we use this routing table, in our example, the destination address is 10.2.1.1. So the longest prefix match for this would be 10/8, because 10.8 does not correspond, and 10.1 either. So the longest that correspond would be 10/8, and we know to transmit to the Eastern interface. Okay, yes?
You said if there is /8, it means that if there is 10, it goes to East.
Yes, it means that...
There is one, the 16,
so no, no. The rule is we don't really care about the ordering of the rules in the routing table, but what's important is that we use longest prefix match. So we will test our address with every rule and see for how many bits it corresponds the most. And 10.1 does not correspond to 10.2, right? So it cannot work. The only one that works, the longest prefix that works, is 10/8 if we check only the first 8 bits. It's the only routing rule that corresponds to our address. But if another destination address arrives and corresponds more to one of the other rules, then it will go to another interface. Did I answer your question? Okay. Okay, so this brings me to the end of what I had to say today.